let's use our area formula again. Here's our formula for surface area. And take a look here. Calculate the surface area of the part of the cone, x squared plus y squared is equal to z squared, lying above x squared plus y squared is less than or equal to 4. So x squared plus y squared is less than or equal to 4. In the xy plane, that is, we're talking about the region, inside the circle here. And so the part of the cone x squared plus y squared is equal to z squared. So what does that look like in 3 dimensions? That our cone looks like this. And that goes, that keeps going on off to infinity. And so the idea here is if you project down, we slice it like at this place right here, the projection down into the xy plane is this filled in circle, this disk here. So okay, we need to come up with a parametrization for this. We need to say r of something comma something is equal to, let's fill in our parametrization here. Okay, so the way that we're going to do this is that we're going to identify points on the surface by what point they project down to in the xy plane. So we want to use our parameters to parameterize points in the inside the circle here, and then there will be a unique z coordinate associated to that. And a little bit of thought should convince us the best way to parameterize points in the projection here in the xy plane is with polar coordinates. So let's say r of r comma theta here. By the way, let me point out here that before I do anything else, I'm using r in 2 different ways here. I don't want you to be confused. This r with a vector hat over it, that means the parameterization, it will be a vector. R without the vector hat over it will be a parameter. It will be the usual r from polar coordinates. So how do we do this? R, r and theta, well, x and y are going to be the usual r cosine theta and r sine theta from polar coordinates. Now, how about the z component? Well, x squared plus y squared is equal to z squared. X squared is r cosine theta squared. R sine theta, y is r sine theta, so we have r sine theta, quantity squared. But of course, this is, using what we know about polar coordinates, x squared plus y squared is equal to r squared, and this is equal to z squared. So r squared is equal to z squared. This tells us that r is equal to z is equal to r. We can take square roots without worrying about plus or minus here because everything is going to be positive. R is always positive by construction, and we want to be lying above the circle, so z is positive here. So here is our parameterization. R of r theta is r cosine theta, r sine theta, and r. This is our parameterization. And we should fill in what are the bounds here. We're going to do 1 full loop around the circle, so theta is between 0 and 2 pi. As for r, x squared plus y squared is less than or equal to 4. R squared is less than or equal to 4. R is less than or equal to 2. R is between 0 and 2. Okay, so at this point then, we want to be able to apply our formula. So we need the partial derivatives of r with respect to u and v, which in this case aren't u and v, they're r and theta, and then take the cross product. Okay, so let's do that right now. R sub theta, Let me go r sub r. The partial derivative r with respect to r, where I'm using r in two different ways there, is going to be cosine theta sine theta 1. R sub theta is going to be negative r sine theta, r cosine theta, and 0. So then, what do we end up with? The cross product will be a hat, j hat, k hat, cosine theta, sine theta 1, negative r sine theta, r cosine theta 0. Okay, so it's going to be I hat times this times that is 0 minus this times this is minus r cosine theta, minus j hat times this, so that's negative r sine theta, minus this times this. Oh, sorry, that should be a plus there. It should be this times this is 0 minus this times this, so that's what we end up with there. Plus k hat times this will give us r cosine squared theta. This times this, subtracting that will give us r sine squared theta. Okay, this will simplify. Negative r cosine theta, negative r sine theta. R times cosine squared theta plus r times sine squared theta is r. So then the length, the magnitude here, is going to be square root of this squared plus this squared plus this squared. And so this is r squared cosine squared theta plus r squared sine squared theta plus r squared. This is r squared, this is r squared, 2r squared under the square root 2 times r. So to finish off the problem, we need to apply this formula here with this as the magnitude of the cross product and these as our bounds. And so we end up with, okay, so theta runs from 0 to 2 pi, and r runs from 0 to 2, square root 2r dr d theta. Note, this is not an example where we are converting from rectangular coordinates to polar coordinates. You know, we had a double integral in terms of x and y, we're converting to r and theta. We don't throw in another factor of r here. So the way that this is constructed is, you know, once we make the choice to use r and theta here for u and v, there's no extra factor get thrown in there. The extra factor comes from the magnitude of the cross product here. Okay, so what do we end up with when we integrate? The theta integral will give us 2 pi. The r integral, root 2 over 2 r squared, plug in from 0 to 2. 2 pi times root 2 over 2 times 4. That looks like 4 square root 2 pi to me.